Hello students, in this video we'll see how to evaluate Bromwich integrals in the case when the Laplace transform has a finite number of poles. So let's be given a Laplace transform. F tilde of z, defined in some right half space, defined for real part of z bigger than a for some a greater than 0. Then I can recover f itself by the Bromwich inversion formula. So then f of t is 1 over 2 pi I, the integral. Let's take the limit first actually, moving the limit first. So the limit first, the limit as beta goes to infinity, the integral from gamma minus I beta to gamma plus I beta of f tilde of z e to the zt dz. That's our Bromwich inversion formula. And under appropriate decay conditions on the function f tilde, which most of the ones that we're going to deal with are going to have that strict decay condition, we can therefore write this as the sum, j goes from 1 to n, of the residues of f tilde of z e to the zt at z equals zj. And here, z1 through zn are the poles of f, where z1, z2, zn are the poles of f tilde of z. Good. Okay. So let's analyze these residues carefully and see if we can get any nicer formulas for this, right? So let's suppose zj f tilde has principal singular part, just the part of the Laurent expansion where there are negative coefficients. That's this principal singular part. Principal singular part b1 over z minus zj plus b2 over z minus zj squared all the way down to bk over z minus zj to the power k. That's the principal part of that pole, right? Good. Now, I want to find the residue, because of course the holomorphic part won't contribute to the residue at all. But now what do we note? We note that e to the zt is equal to what? Is equal to the sum, n goes from 0 to infinity. I'll say m. I've already used n over here. M goes from 0 to infinity. And then I'm going to do the I have to do the mth derivative of this thing at z0. Well, the mth derivative of this thing at z0 is just going to be, if I do m derivatives, this is going to t downstairs, right? So this is going to be t to the power m, e to the what? E to the z0 times t times z0, right? Over what? And we can say j actually. So let's put a j there, because we're going to do this at zj. There we go. So let's put zj. And then over m factorial, and then z minus zj to the power m, okay? So now I can compute the residues of these things, right? So now what am I going to do over here? So I can pair each of these terms, because these terms are over here being hit by these terms over here in this expression, right? So what is the residue? Hence the residue of f tilde of z times what? Times e to the zt at the point z equals zj is going to be what? Well, let's see what happens over here. So the first term over here is going to be the t to the 0 power over here. The t to the 0 power is going to be the coefficient of just this what? That means there's nothing to hit that b1 over here. So that's 1, it hits with an e to the tj. So that's going to be a b1. And then everything's going to have an e to the tjz in there, right? And then what will the next term be over here? Now, to hit this b2 term, I need 1 power of m, right? So I need a t to the power m with m equals 1. So if m is equal to 1, what are we going to get? We're going to get a t, an e to the t zj, a b2, and then a 1 factorial, right? And then all the way down to what? I would need what? I would need m equals k minus 1 to annihilate that thing. So m equals k minus 1. So down to the very last thing over here, down to the t to the k minus 1, e to the t zj, and then what? And then b k over what? Over, I need k minus 1 factorial. K minus 1 factorial like that. Excellent, okay? So if we simplify this, to each of the e to the tj, so what we get is the following. We get this expression, we get this is equal to e to the t zj, and then what? And then times b1 plus t b2 over 1 factorial plus t squared b3 over 2 factorial, all the way down to t to the k minus 1 times bk over k minus 1 factorial. So that gives us a useful way of computing residues like that, okay? So let's see an example of this. What will be an example of this? Example. Let's find the inverse Laplace transform. The inverse Laplace transform of 1 over s squared plus 1. We know this is going to be sine. Let's see how this is going to work, right? So there's two residues to compute. This is going to be the residue of e to the st over s squared plus 1 at s equals I, that's a singularity, plus the residue of e to the st over s squared plus 1 at what? At s equals negative I, okay? So let's compute those residues and see what we get. Well, the first residue over here is going to be what? It's just going to be the function e to the st over s plus I evaluated at s equals I. This next residue over here is going to be e to the st over s minus I at s equals negative I, okay? And so what will this give us? This is going to give us what? This is going to give us an e to the it over 2I minus, of course, because there's going to be a minus down there, e to the minus it over 2I, which is e to the it minus e to the minus it over 2I. And that gives us what? That gives us sine of t, right? And we knew that to be sine of t, right? So it's just a remark, note. We already knew from first principles, from our course in ODE, that the inverse Laplace transform of 1 over s squared plus 1 is sine of t, and that just follows from Lorentz theorem, right? Okay, so the Lorentz theorem on uniqueness says that I can Laurent expands, and basically I'm doing the same thing in ODE. I'm Laurent expanding these things and saying the Laurent expansion coupled with the polynomial result, gives me that this is going to be sine of t, and then Lorentz theorem says it's unique up to a set of measures 0. So that closes the book on that. So in other words, what we're doing over here is from the standard ODE methodology, the power series methodology for inverse Laplace transforms is identical to this, and there's no coincidence there, right? I'm using the analytic extension of the Laplace transform, then I'm using the residue theorem, which is a summation method, which is a result about convergence of power series, right? So the Cauchy theorem is a trivial consequence if there's a power series expansion, right? So in other words, under the right decay conditions, I can use the Bromwich integral, and in this case, it was fairly simple, but we'll see in further videos more complex examples of doing inverse Laplace transforms of this Bromwich procedure, which is much easier than doing convolution or partial fractions or some other series method for finding inverse Laplace transforms. Thank you very much.